In this lecture, we will be covering direction fields. A direction field is an equation, a function where we have a y prime, a function, a derivative of a function, in terms of x and y. And using this, we are able to plot the entire possibilities for this function. We will have multiple slopes at every different point. As you can see in this example, we have different kinds of slopes in different points. And if we draw a line on these slopes, we have potential functions representing our function that satisfies the slope field. So when we express differential equations of first order, we usually actually have slope fields, and when we find our c values, our c coordinates, our c values, we are actually finding a particular curve among this direction field. So a differential equation is actually a way we can use the direction fields to describe a differential equation. And for example, we have this differential equation. If you want to solve this, you can use separable. Separable method would solve this differential equation, y prime equals to 1 over x. And if we plot the derivatives, the points of this function, we will get this curve. For example, let me try to show you guys. If we have, first of all, our 0 is not a defined point, because if we plot 0, 1 over 0 is an undefined. As you can see, we have a vertical asymptote on 0. So every point on 0 should not be available for us. We don't have a slope there. If let's say x is 1, right? When x is equal to 1, which is this vertical line over here, we will have a slope of 1. So every time we have a 1, we do have some kind of a slope of 1, okay? As you can see over here on the left side of the graph. If we increase our axis, our derivatives get smaller, which means our slope is decreasing by time. So as gets larger and larger, our slopes go and get almost like a horizontal line. As you can see from the left side of the graph, they get smaller and smaller because the y prime gets smaller. And if we introduce negative x's, our first will be -1, so we will have a steepest -1. And then if we decrease the axis, we will actually be decreasing its magnitude, and the magnitude, when it will be still negative because we still have negative values, but it will get less and less steep every single time, as you can see on the left side of the graph. So when you're plotting direction fields, all you want to do is plug some x values and maybe y values. You might have a function of y here also, and depending on those inputs, you want to determine your slope. For example, if my slope is a positive, obviously I should have a positive slope, and if it's a bigger magnitude, it should be steeper. If it's a smaller magnitude, it should be smaller. So all you have to do is basically draw these plots, and usually a few points on to describe the behavior of the function is important. So for example, this we can actually kind of see our function on the left side of this will be curves like this, okay? And on the right side, we do have similar curves, just that it's like symmetric around the vertical axis. So you'll have to be able to make some of those determinations. And if you draw a clear plot, more organized plot like the one on the left, you should be able to graph these curves very smoothly. Now we have a very nice problem. We are asked to find a direction field of this problem, dy over dx equals to y. So first thing we want to do is to put this on the Cartesian coordinate system. And after that, what you want to do is, since these are only dependent on y, our x will not have any impact. So our slopes will be consistent along the horizontal axis. So over here, when y equals to 1, we will have a slope of 1. Okay, these are not supposed to be entirely accurate. It's completely okay if we have a little bit of a flaw, which is really understandable because you're just drawing it by hand. Okay, so you just need to give the idea to your professor. So as y gets larger, for example, y equals to 2, we have a larger slope. That's why we get more and more steeper every time we increase our magnitudes. Okay? And finally we will have very like steeper and steeper as y gets larger magnitude wise, because on the negative side we will have a negative. Let's say this is a -1. Okay, we will have something like this, and as it gets like this, it gets more and more steeper every single time. And finally we get like really steep. Okay, like this. So basically you are able to see a very nice picture. If you can connect some of the lines here, we will see a nice picture of the potential solutions for this direction field. And very importantly, over here at 0, our function will not have any slope. This means this is one of the important points. Y equals to 0 will make this slope 0. So sometimes problems may ask you some tricky questions like this, and usually what they're testing is, do you understand what happens when the direction field is equal to 0? How does that happen? And how does it look like? So basically you just want to put the zeros. Especially zeros are important because most of the time zeros are changing the behavior of this function. For example, over here on the top side of the 0, we have a positive slope, and over here we switch negative slopes. Okay, so that's a very important note, and that's gonna happen most of the time. If we had another 0 here, our slopes would potentially change to the other direction. I'm not saying that would always happen, but there might be different cases, but it is very common to see in these direction fields. So always note what zeros are, and be open for changes at the 0 point. Now we have another interesting one. We are asked to sketch a direction field, and dy dx is now equal to x. So this means our y has no impact on the solution, so our solutions will be vertical wise. And let's say x equals to 1. So our direction fields will be just like 1 over here when x is equal to 1. Okay? And as x gets larger, our slopes get even steeper and steeper. So I'm going to try to draw as the best of my ability. Okay? And we will get more and more steeper every single time. And at x equals 0, obviously we have straight lines like this because slope is equal to 0. Okay? And one more important thing to note, if we have some undefined value, we usually see asymptotes for dy dx. For example, in the first example, we had a 1 over x, and when x was equal to 0, we had a vertical asymptote. So we might get horizontal or vertical asymptotes depending on the undefinedness of the function. So we should also keep an eye on those. Okay, and for negative x, let's say -1, we will have -1 slopes, just like this. Not great at drawing these, but it's okay. As I said before, you can, like, it's not supposed to be perfect. It's okay if it's not perfect. I mean, it's very nice to see it visually. It's gonna be more helpful if you can draw more precise one. But yeah, it is important to get the idea to the reader. Like, I should be able to tell that this slope is steeper than this slope, which it is, right? This is more of a steeper slope than this one. So it is important to just show that these are getting steeper and steeper, and all of them don't need to be like entirely accurate, but you just need to show the idea. And like when I watch this, I should be able to say, oh, this looks like something like this, right? And it is true. They are some like parabolas and stuff. And it is just important to give this accurate picture. And from this picture, when you want to solve these, you get pretty much every single potential option, and this like goes on to infinity. from the x and from the y-axis. So you get infinite amount of slopes, which is why it's called a slope field. And yeah, I mean, you can grab pretty much any slope and draw a line and pretty much understand every single line depending on your initial value. If we give you, like, for example, if I tell you our slope line passes this point, okay? We actually just can immediately tell that which point the slope belongs to, okay? So, yeah.